Hi, chemistry students. This is your lesson on empirical and molecular formulas. So we've been talking about in previous lessons about percent composition by mass. So how is percent composition used? By decomposing compounds and analyzing their percent composition by mass, scientists can identify the molecular formula of the compound and therefore identify an unknown. So this is an important tool in investigating unknown compounds that may be found in crime scenes, in water supplies, in a variety of uses. So first of all, let's review a couple of things and learn a new term. First of all, the molecular formula shows the ratio of the elements in a compound. But we also have something called an empirical formula. And let me show you an example. What do you think an empirical formula is? A molecular formula would be C6H12O6, and the empirical formula of that molecular formula would be CH2O. So by looking at and comparing the molecular formula with the empirical formula, what do you think the definition of an empirical formula is? That's right, an empirical formula is the lowest whole number ratio of the molecular formula. Good job. So, let's test. The empirical formula for C6H12 would be which of these things then? Decide on your answer or pause the video. That's correct. The lowest ratio between 6 and 12 would be CH2. Just find the greatest common factor, which is 6, and divide it into the 6 and C and the 6 and 12, and you get the empirical formula CH2. Here's another example. This is a molecule called benzene. Looks like this right here. Benzene is a chemical widely used by the chemical industry. It is also found in tobacco smoke, vehicle emissions, and gasoline fumes. Exposure to benzene increases the risk of leukemia. So if this is the molecule, benzene, by looking at the molecule and counting, you should be able to figure out what the molecular formula of benzene is. And that's right, it's C6H6. There are 6 carbons in this thing called a benzene ring attached to these hydrogens. But can you also figure out the empirical formula of benzene? So what is the empirical formula of benzene? If the molecular formula is C6H6, what is the empirical formula? You're right, it would be CH. All right, a couple more practice questions. Here is a molecular formula, C6H12O3. What is the empirical formula? And here's another molecular formula, CO2 for carbon dioxide, and what is the empirical formula? Now, it should be noted that all ionic compound formulas are the empirical formula because they're always the lowest ratio of ions. But for this one, the greatest common factor of 6, 12, and 3 is 3. So if we divide 3 into the 3 here, 3 into the 12, and 3 into the 6, we get C2H4O as being the empirical formula of C6H12O3. Now, for CO2, the empirical formula is simply CO2. Sometimes molecules are at their lowest ratio, just that's the way they're put together. But again, ionic compounds are always empirical formulas. So this distinction between molecular and empirical formulas has mainly to do with covalent compounds. All right, so let's do a chemical analysis question. A compound has an empirical formula of CH3. Its molar mass is 30 grams. What is its molecular formula? So you can imagine that you are a lab boss and you have a couple of technicians who are working for you and you have an unknown compound. They have been able to determine that the empirical formula of this unknown compound is CH3, and they've used something called a mass spec to figure out the mass of this compound is 30 grams. And using those two pieces of information, you should be able to figure out the molecular formula of this particular compound, and hence probably what its identity is. So the first thing you're going to do is figure out the empirical mass of CH3, really the molar mass of this empirical formula. And then you're going to see how many times it goes into the known molar mass of this compound. And then by doing a simple multiplication, you should be able to figure out the molecular formula. So let's just go through this one. So first of all, the empirical mass of CH3 would just be 15 grams. Carbon is 12, each hydrogen is 1. Okay, so that would be 12 plus 1 plus 1 plus 1 would give us 15 grams. Now we know that the actual molecule has a molar mass of 30. So 15 goes into 30 2 times. That means we are going to have to multiply this empirical formula by 2. And again, in this case, we're going to be multiplying the subscripts. And so the actual molecule itself would be C2H6. Now you can double check yourself. C2H6, carbon's molar mass is 12, so 2 times 12 is 24. Hydrogen's molar mass is around 1, so 6 times 1 is 6. So 24 plus 6 is 30, and that is indeed the molar mass of our unknown. We also can see that this C2H6 could be reduced down to CH3 as an empirical formula. So we verified that the compound that was brought to us that perhaps was an unknown must have the formula C2H6 to meet the 2 criteria in this question. Okay, so let's have you try one. A compound has a molar mass of 70 and an empirical formula of CH2. What is its molecular formula? Okay, so in this case, you're going to want to, again, figure that you are the lab boss and your technicians have brought you these two pieces of information about this unknown molecule. They figured out that the molar mass is 70 and it has an empirical formula of CH2. So you're going to figure out the molecular formula. Do you remember the steps? Well, the first thing you're going to do is figure out the formula, the empirical mass. So carbon is 12 and each hydrogen is 2, giving us 14 grams. We're going to see how many times 14 goes into the molar mass of 70. That's 5 times. And so then we will multiply the subscripts by 5 to figure out the actual molecular formula. So that would be C5H10. Now you can verify that this makes sense. See, 5 times 12 is 60 plus 10 times 1 is 10. So that does indeed add up to 70. And we can also see that if we divide both of these by 5, we get CH2. So this also matches the empirical formula. In fact, this is a compound called cis or trans, depending on how the hydrogens are arranged, 2-pentene. Pentene, 2-cis-pentene. It is a carbon chain of 5 with 1 double bond. So you have identified this based on the information brought to you. Okay, now there's one more type of empirical formula problem from percent mass that you're going to have to master. And this is really cool because once your lab techs have essentially burned and figured out the percent mass of hydrogen and carbon in any hydrocarbon, or really any formula, you figured out the percent mass, you can find out what that molecule, what the empirical formula is. And then if you have that additional piece of information from the mass spec of the molar mass, you can really identify the compound. So we're going to go step by step through this problem. What is the empirical formula of a compound that is 7.7% by mass hydrogen and 92.3% by mass carbon? So you're going to want to write this down because you're going to do one yourself after we finish this one. So first of all, you're going to pretend in that formula that percent is grams, which makes sense. If you have 100 grams of it, how many grams are hydrogen? How many grams are carbon? So if we have that, we have 7.7 grams of hydrogen and 92.3 grams of carbon. Now, the ratios in the formula have to do with number of particles. So our good old friend, the mole, is going to show itself again, and we're going to figure out how many moles of hydrogen that is and how many moles of carbon that is. Okay, so we're going to determine the moles of each element. If you recall from the mole road, you look on the periodic table and you find a dimensional analysis conversion factor. We know that 1 mole of hydrogen has an atomic mass of 1.01 grams, and 1 mole of carbon has an atomic mass of 12.01 grams. We can figure out the moles of hydrogen and the moles of carbon in 100 grams by simply doing a division. So 7.7 grams of hydrogen divided by 1.01 grams of hydrogen gives us 7.7 moles of hydrogen. And then 92.3 grams of carbon divided by 12.01 grams of carbon gives us just about 7.7 moles of carbon. So what you can see here is, even though the grams look very different because hydrogen is a much smaller molecule, we have in this compound actually the equivalent number of hydrogen atoms that we do to carbon atoms. So that is what's going to tell us the empirical formula. Now the next step here is just to take this 7.7 and divide each one. We're going to basically normalize it, make sure that it's a 1-to-1 ratio. So in this case, it doesn't matter which one we do. We usually take the lowest one and see if we can see the ratio. This time we're going to divide each of these by 7.7 to see that the ratio here is 1 mole of hydrogen to 1 mole of carbon. And the lowest ratio between the carbon and the hydrogen is 1-to-1, so our empirical formula is just 1-to-1, or CH. Okay? Let's try one other one. What is the empirical formula of a compound that is 20% by mass hydrogen and 80% by mass carbon? Again, you're going to want to go through each one of the steps that I told you. You're going to pretend the percentage is grams. You're going to determine the number of moles, and then you're going to determine the whole number ratio of the whole number ratio by division, and you're going to write the empirical formula. Okay, so let's try that one. So first of all, you're going to pretend the percent is grams. So instead of having 20% and 80%, we have 20 grams of hydrogen and 80 grams of carbon, which is if we had 100 grams, that's how much we would have. Again, we're going to remember 1 mole of hydrogen is 1.01 grams and 1 mole of carbon is 12.01 grams. We got those from the periodic table. We're going to determine the number of moles of each element. So 20 grams divided by 1.01 is just about 20. 80 grams divided by 12.01 grams is about 6.67 moles of carbon. So you can see now the ratio is not 1-to-1. We have more moles of hydrogen than we do moles of carbon. So we are going to do a division. We're going to divide 6.67 into both of these to normalize the ratio. Okay, so we'll divide 6.67, and that goes into 20 just about 3 times. And 6.67, and that goes into carbon, 6.6 moles of carbon, just about 1 time. So the ratio here now is 1-to-3, 1 carbon to every 3 hydrogens. That means that our empirical formula will be CH3. Now you're going to get plenty more practice on this, have some more problems, and we're going to do some more examples in class. But these are really important chemical analysis problems that chemists use every day as they are identifying unknowns out in the field.